Hello, everyone. Welcome back to the last tutorial where we will have new content here in ECON3350. This is our tutorial 12 about multivariate processes 3. It's pretty much because week 10 and 11 were compacted inside of week 11. So we have 1 and 2 during last week, and this will be the third one. Okay. And it's also that point of the semester where we start asking you guys to leave a review to answer the SE tutor. So if you found these videos useful, if they were helpful, please take the minute to just leave a review there. And if you didn't, also feel free to let us know that how we can improve. You are eligible, like you can leave a review for more than one tutor if that's the case, if you attended more and you feel like leaving. And you don't need to be enrolled into it. So like the videos are in theory the external ones, but I to my knowledge, I think a lot of internal students are doing that. So you can leave SC tutor. So yes, please leave one. Thank you so much. But well, on a different topic, let me just set the link here for people that are online now. On a different topic, report 2 is available, as I said last week. You probably have seen, and it's based on it is multi-equation, but you will see that the data set is very similar to what we had before. A few things we are still marking your report 1, and a few things I've seen. I hope I can give you a little bit of feedback to help with report 2. So you have here report 2. There will be 2 questions with 50 marks each. First thing, the length. You can probably have a good answer with 1,000 words for each question, I would say, maybe a little bit more, but that would be reasonable. You can find it straight to the point, but there is no penalty for writing more if you feel like. We are receiving reports up to, well, actually more than 9,000 words, very long ones, which I imagine take a very long time to write. I just thought maybe you would like to know that you probably can answer these things with, I'm guessing 1,000 words per question should be enough, but maybe 1,500, maybe, depending on. I'm sure we got really good reports that were 2,000 words total. So yeah, also amazing reports that were much longer than that, of course. Another thing that I wanted to call your attention is the following. If I have 10 marks to distribute on model identification, make sure you describe your model identification kind of step by step. Don't put the output of R, this kind of thing, but at least at a high level, describe what is happening. Don't forget steps that we're doing. That's important. Forecast computation, I'll probably look at your plots, but also some people put some tables, which were pretty cool. I think it's nice. I can have a look at the numbers, but quite important to have the plots. So if you haven't done that, maybe for report 2, consider doing the plots. At least it shows me you know what you're talking about, and you can fit things and you put in the plot and etc. And you can use the code that we showed you how to do. Evaluation and comparison. Now, the new thing for report 2 is that we will be comparing it with the results we got from report 1. So look at this. Use the observed CPI inflation data from 2022 and quantitatively evaluate and compare forecasts generated by our multiple equation that we do in report 2 with your research report 1. Okay, so you might have to bring the results back from your report 1 into your report 2 to make a little bit of a comparison to see if now that we're using a multiple equation, if there was some improvement. So forecast evaluation and comparison, prediction and interpretation. Both things make sure you cover them. I noticed that a few students forgot for report 1 to write the motivation, and then there was the conclusion. And the conclusion, somehow, of course, it explains a little bit of the motivation, but I have 10 marks to give for motivation, 10 marks to give for the conclusion. So if you just had one paragraph explain the results of the report, even if you said that it influences the RBA decisions and etc., there's not much of a motivation. It's not saying, oh, how important it is to forecast inflation. So you might have lost some marks in case you haven't put motivation, and the other way around also with the explanation, right? The only one that I can't like really explain you how to do writing and organization, just make sure it's neat, a secret, kind of secret, but not secret at all. It's like I have Grammarly in my computer to avoid having some typos. It points out where you have typos, but other apps might help you with that. You can check on Word if you use in Word. Some things. If you have a lot of typos, you might be missing marks here, but not for one typo or 2 typos. I don't think you will miss anything. Okay, so just wanted to tell you that just a little bit, just a few things to pay attention to. 50 marks each. You will see question 2 starts here, but then it continues. In addition, please compare the dynamic effects with the rest of the things. Today, we will be mostly talking about dynamic effects. We talked a little bit last week. Today we'll be talking more, and I hope this tutorial will be very useful for your second report. Okay, so let's continue. Let's go back to our tutorial. So your report 2 will be due on the 5th of June. So you still have more than 2 weeks, right, to solve, and that's it for report. Also, you have your quiz 4 available. If you haven't submitted it yet, you have until Friday before 4 p.m. this Friday. So good luck with it. And let's go. Tutorial 12. We will be talking about, let's just save the term structure.csv that we have. It's the same data set that we used for tutorial 6. So you'll see how similar it is. So you have the tutorial PDF, and I have the code in the same code share structure. So 3350_12 this time. So let's click that. Get that code. You should see something like that. I will just copy everything. Let me do something today. I think it's the first time we're using Orca package. So we might have to install, you might have to install in your computer. I'll just leave it like that. I think it would be better. Let me open my R. And we will start from there. I will close this one. Let me do the same for my original one. Save, close. And now let's open a new R script, paste the whole thing here, in here. And also very important, save this R script in the same folder as we have our term structure, which for me it's here, 3350 and tutorial 12. Tut 12 live, for example. All right, that's it for R. Let's go back to the slides. So today we will be talking about a vector error correction model. We had a vector autoregression, and we talked about error correction model before. It was pretty much getting our ARDLs and reorganizing it in a way that we could see some short run and long run multipliers, right? Now we're doing the same, but in a vector way. So our VARs were autoregression functions, but with distributed legs, so different variables, right? Which we're moving, it's just adding a vector before each of them kind of thing. So ECMs, we transform them into error correction models. So construct an adequate set, obtain inference on equilibrium relationships for vector error correction models. So these relationships and equilibrium relationships, as you remember, will be in your report too. And use R to obtain inference on dynamic relationships from identified structural vacuum. Let's go. First, problems. The data file term structure contains data for Australian interest rates. As you might remember, we have the bond rates for 5 years and 3 years, which we will call capital market rates, and the short term, or 6 months or 3 months bank accepted bill, which will be our money markets rate. And the data consists of analyzed monthly rates for the period of June 1992 to August 2010, a total of 219 observations. Let me go one ahead. We're doing just the basic, load the libraries, and then load the data, and creating variables, then add all of them to X, right? So let's go. Here, I will first clean everything, remove everything. You probably have to install Orca. Then let's load our four libraries. Then we're setting our working directory so we can load term structure. Once again, just the basic read the lim with header. It's a CSV, so comma separator values, comma as a separator. 219 observations of 5 variables. If you click there, you will have all these observations. Like the 5 of them will be, one of the columns are the dates for as per usual in our time series, and the other 4 variables there. So first, for the date, you saw we had an M in there, right? So we want R to understand it. We'll have to translate it a little bit for them. So dates will receive as year, month, not quarter this time. And we're translating as we did for report 1. We're telling them format equals to first percentage capital Y, because it's 4 digits year. Then there is an M hanging in between the year and the month. That's why we have a capital M there. And then percentage little m, which is just the month. So after doing that, you see the dates now, it's interpreted as a month and a year. So it means I understood what we have, right? T is just the length of our data. So, and you will see why we're doing that. 2019 observations. So T has 2019. It's just a value to 219. Sorry, 200. N equals to 4. We can change it. We can also call it. Should I change it? Yeah, we can leave it like 4. It's the amount of variables we will have. But I can add something here. If you have something different, N is equals to the length of X. Length of call names, maybe, of X. Let's see if it works later. So N receives 4. Then we will have pretty much the same as we did before, but there is a minus T there. And why is that so? If you open your data set and scroll it down to the end, you will notice that our short-term rates don't have the last observation. So the 219, it's not there, just for I3Y, I5Y. So what we're doing here, we're subtracting the data in the position 219. Remember, when you do a plot of difference data, we do a -1. So we're taking the one in the first position. In this case, we're taking the one in the position 219. So we're subtracting for all of them, and the rest is there. So you will be able to see that it has just 218 elements instead of 219. Finally, we put them together, and let me have a look if this is going to work. First, call names. Oh, you cannot, sorry. It says in my computer that it's screen sharing, but let me stop share. and share screen again. Can you see my R now? Ah, perfect. Yeah. Ooh, apologies for everybody in this recording. I think what I'll do, I mean, I'll just start it again. Maybe not. Maybe it's not starting again. I'll start explaining it again. I think it makes more sense because it's a little bit too much. So apologies for that. You had to hear a little bit without looking at the R. Let's go again. So first we removed everything, right? Clean. Then probably you installed Orca. Then we load the libraries. And I was explaining all of that, set working directory, data, then the dates. Let's go again. So you will see that the dates have an M here. So it's year, then month. Then we will have dates here. We will use as year, month. And then as I explained, for this, let me print it again here. For this year and month with an M in the middle, we will use the format. We're kind of translating it to R, percentage capital Y with the year. Then this M that sits in the middle is there. Then the small percentage M in for the month, right? For these 2 digits we have afterwards. So when you run, you will see the dates is showing the month and the year. So it means are understood. The T is getting the length of dates. So it's just 219, which is the number of observations. And it's 4, which are the 4 variables that we have in there. Finally, we are adding all of them as we did before, just getting one variable and putting into an R variable for each of them. So I90D or I180D, but we are subtracting the item in the T position or 219 because it's missing here. It's missing in this last row. So we're just eliminating this line, which means when we run, you will see that we just have 218 lines. Okay. Finally, I was going to try something here with n call names of X. Let me see. Oh, sorry. Let's put things together for the X. So if I put a call names, we have 4 of them. If I take the length, will be 4. We could also have this line and receives length, which would be a 4. This, instead of setting it here, you can use it here. In case you're doing the same thing in your assignment and it's not 4, you could do something like that, for example. Let's go then. Sorry for the hiccup of not sharing the R. I think when I open it after recording, it doesn't share automatically. Now, first, consider a var model of the multivariate process xt, where xt equals to the 4 variables that we had before. Construct an adequate set of var models specified by the live length p. This is nothing new for us. We've done it last week. So it will be the same process that we had before. So let's go. Question 1. So first we create a list of vars. Then we will create an information criteria matrix, IC matrix. For our var, it will have 20 rows and just 3 columns. These columns will have 1 for the amount of flags from 1 to 20, then the AIC score and the BIC score, right? Finally, we will run it. So inside of a 4, we'll have the P running from 1 until 20, and we will have varied var estimate. It's this list of vars that we created here. We'll be receiving var with our X and then P, the amount of flags for each of the things. Then our matrix will receive a concatenation of the amount of legs, the AIC score for that specific model, and the BIC score for that specific model. So let's run it. As usual, var runs really quickly. And let's take once again, the best. This one will get the best AIC, best BIC. If you click, it is sorted 3, 4, 5, 6, 2, da, 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 da. And for BIC, 2, 3, 1, 4, 5, 6, 7. What we're moving on with, considering these two ranks, would be the ones vars with legs 2, 3, 4, and 5, because they are in the top 5 of both. And the rest is quite a bit inferior. You will see quite a difference. After these 4 guys, there's quite a jump in score. Where is it? Here. Actually, the jump is already happening from 6, and in the BIC, kind of a gap here, right? Then 1, 2, 3, 4, 5. Then the BIC is a massive jump. So I would say in the BIC it's much worse. It's coming from this and 100, 1,189 down to 116, 100,016. So yeah. That's what we're talking about. And then let's get our adequate set. It's just taking in our matrix from 2 to 5. And then finally, adequate index is just 2 to 5, 2, 3, 4, 5. All right. When we do a var, we're doing vars, we check to check the residuals. Instead of doing the Young box test that we did before, we're doing the Bruch-Godfrey test. So this is how we're running it. We have a number of models, which would be 4 of them, 2, 3, 4, 5. And there you go, number of models, just 4. And we're running the 4. Let me have it printed down there. Which first, we'll just take how many index, how many legs we're using. When you put it in P, just printing the name, checking var 3, for example, and then print a serial test. This is the function we're using for our specific model, plus legs of the Bruch-Godfrey equals to 1. Here we're specifying how much we're testing, and then type equals Bruch-Godfrey for the test that we have. And these are the results here. You will see very small p-value for var2, and then good values for the other 3, which I have, well, not so good for var4 actually, as you can see here, but we'll still move on with it. Look, I printed it, I put a green, maybe I should put a yellow for this one, but you will notice that we will be moving with 3, 4, and 5. So for the Bruch-Godfrey, during this, we could notice we're making a little bit of exception when it's between 1 and 5. I might change the color for this one for the future, but definitely not this one, which is very small. All right. And that's it. We're going with 3, 4, and 5 legs. That's it for our question 1. Oh, just going back there. Now, using the adequate set constructed in question 1, implement Johansen's trace test to obtain inference on possible ranks. Rank A1, da da da. What does this suggest about possibly expanding the adequate set of var models to include restricted VECMs or VECMs, vector error correction models? So the R's and the rank, right? What are we going to do first? First, we're going to look at if our var is stable. Remember the last week we had eigenvalues that were higher than 1. It was a tiny bit more than 1. This time is not the problem, as you will see here. It is a little bit smaller. So where is it? Check. We've done that part. Okay. Question 2. I'll set this adequate set var from 3 to 5 instead of 2 to 5. Now it's just 3 to 5, just 3 models, and adequate index var 3 to 5. Now, for the roots, for the eigenvalues, we will use the function roots as we did last week. So number of models should be just 3 now, because we remove var2. And we will run this for that will go from 1 to 3. We'll get the leg, and then print paste 0 var the p maximum absolute eigenvalue is. We're taking the max and then running roots from the package vars for that model. Pretty simple. The thing itself returns many eigenvalues. I think I showed last tutorial, but where is it? Oh, how many things do I need to consider? Maybe this amount? Yeah, there are many eigenvalues, but the most important for us is just the maximum one. So that's why we're running it like this. Let's run it again. So these 3 guys. Now, let's go back to what we did in the past when we were single variate. We were concerned when our alpha was equals to 1 or very close to 1, our alpha 1, the one that was multiplying the variable t minus 1, right? Because if we had a random walk where alpha 1 is equals to 1 or a bigger than 1 value, our forecast would explode. Now, this version of multivariate, it's related to our eigenvalues. If we have eigenvalues relatively close to 1 or bigger than 1, our forecast, as we mentioned last week, will end up you have a risk if you forecast for a long period that it will explode. It won't be really precise anymore. So given we have eigenvalues, although we're saying our var is stable, we have eigenvalues relatively close to 1. So we will run another thing, the Johansen's trace test, to evaluate if we should do some vacuums with restrictions on it. And this is how we're going to do. Oh, let's go back. So here we have the number of models. It will be, once again, 3 models, nothing changed. But inside of our for, and I will print it already, we will have the following. First, get the p, as we did before, print, paste, var, blah, blah, blah. So we're just indicating which var we're analyzing first. And then we're printing the summary of this function, ca.joe for Johansen. And we will have ca.joe here, Johansen procedure for var. Inside of it, we have both eigen and trace tests. We're telling them we want to do a trace test. And we want x to be, okay, we want the data we're doing this Johansen procedure test. We're putting our x, right? Our vector of data. And in the k that they have here, the leg order of this series, we're indicating for each of our models that we're moving on, how many legs we're using. So k equals to p, right? So in this case, we had just 3. It was 3, 4, and 5 legs. So let's go. Look at what it returns. Johansen procedure, then test statistics, trace statistic with linear trend. It's quite a lot of things. In this last tutorial, the only thing we will be looking is the following. Look at this for var 3, var 4, and then we will have a look for var 5. The only thing we want you to focus is on this one, this part in here. So this is a test to say, is the number of restrictions equals to 0? Should we consider it equals to 0? The test says 100 returns you a kind of, it's not a t-test, but let's say the test returns a value. Think about the t-test or f-test. 102.5. And you will notice it's higher than the 10% threshold, 5% threshold, and 1% threshold. So it is rejecting in all those levels this null hypothesis here. Then restrictions being smaller or equals to 1, we're also rejecting for the 3 levels. So in 10, 5, or 1%, we're rejecting. Then for restrictions being 2 or less or equals to 2, then we have I'm saying restrictions, I'm sorry, I think I mean rank. The rank of the matrix being like that, the rank being smaller or equals to 2, then we have we pass at 10%. We do not, sorry, we reject at 10%, but we don't reject at 5%. That's it. So from here going to here, look the options we have for rank. It's pretty much the same result, but now we don't, for the var4, we are not rejecting at 10%. And when we go to var5, you will see the same results. It does reject the rank being equals to 0 and rank being equals to 1 or smaller, but it doesn't for 2 and 3. So look, these are the results pretty much for the three, for p equals to 3, 4, and 5. We have rejected all the levels, even at 1%, that the rank is equals to 0, that the rank is equals to 1 and smaller, which encompasses both of this. So we can say it's probably not equals to 1, we reject it. And we are not sure the rank is equals to 2, but we cannot reject the null hypothesis that this is the rank. So it could be 2, could be 3, could be 4. And that's how the Johansen procedure works. It's giving us some advice on what rank should we be considering for our VECMs or VECMs or vector autoregressions. And that's what we're going to do. Look, however, since we cannot reject for R reasonable consider vacuums with R equals to 4 and R equals to 3 as alternative specifications to each unrestricted var, which in our notation is equivalent to vacuum P4. So, important thing to remember. Let's go now. We're talking about vacuum. Let me see what comes next. Is already question 3. So construct an adequate set of vacuum models specified by leg length P and rank R. All right. Let me see if I can add just a little bit. I'm not doing a super crazy theoretical part, but I think I have something open here. Our vector error correlation model is this. Remember our var, when we run the var function, we get this reduced form var in here, right? Intersection, and then for each of the legs, we have a matrix of things. Error correction model is a reorganization of it. And remember a few things about the error correction model. We had a long run multiplier and we had short run multipliers. Also, one thing to remember is this delta xt. So now we instead of having the values, the variables, we have the change, which for us, usually you shorten one leg, because now we're looking at, I was going to say, we were looking at a specific number of legs p, now will be p minus 1. So you will notice that this xt minus 2, now it's shortened to xt minus 1, and this will be important later. Very simple. Okay, construct a an adequate set of vector error correction models specified by like length P and rank R. A few things here to constructing vacuums. Let's go. Quite a long explanation for that one. You have everything here in your answer. Okay, question 3. We are going to consider a few different things. So first, let's create a new list. So vacuum estimate creates a list, information criteria. Now we have 4 columns. Why is that so? We will have the amount of legs that we had in our var, but we will also have the rank for that vacuum. So we will be considering from 0 until 4 vacuums with rank 0 until 4, and then we take the AIC score and BIC score, and I will receive 0, and we will be incrementing this I for every loop. This I is just pointing to which row we're doing the matrix, right? As we did before. So P, now the legs, remember we had from our models were 3, 4, and 5. In this case, it is we're not considering vacuum with 2 legs anymore, because we have rejected the residuals for var2. So it is the same way that we rejected the residuals for var2, it's equivalent to consider we're rejecting for vacuum with 2 legs too. It works. You can deal with them the same way. But it is not unreasonable to consider higher legs, a little bit higher than what we were considering, because probably you remember that 6 legs was not too far in our rank from 2 to 5. But now that we have more restrictions, so having lower ranks lower than 4, means we're imposing restrictions. Therefore, more restrictions, we have less coefficients. Having less coefficients, probably our AIC and BIC can improve a little bit. So that's why you will see that we will be considering legs from 3 until 6. Okay, then we are running R will be rank from 0, rank where is it? Did I not create? N, from 0 until 4, which is the number of variables we have. Let me run the whole thing. And let's go little by little there, what we're doing. So if rank is equals to N, that means rank is equals to 4. It means we're just doing exactly the same as looking at the var for that amount of legs. So let's say the first run, we're coming with number of legs equals to 3. And let's say this is not the first run, it will be the last one inside of 3 legs. But if it's equals to 4, it's just the var of 3 legs. Oh, sorry, var of our data set X with 3 legs. So if the rank is equals to the number of variables, then we have exactly the same. Let me see if I can refer to you. It's how we explained in the previous question. I don't know if we will be pointing out here. There you go. A little bit, yeah. This is the situation. We are considering that all of our things, all the variables inside of our xt are I0 in this case here. It's just the var the way it should be. But the other one, I think the most interesting one to have a look, not the most interesting, but more interesting than that. If we're considering our rank is equals to 0, then what we're doing this vacuum is actually just taking the same var for a difference of X with 1 less leg. Because what is going on is the following. Look at this guy here. We're saying that this one will be equals to 0, equal to 0. Therefore, we just have the same var in here for the diff. So the diff in x in here is equals to the regression, but for one less leg, because now we have just t minus 1, and here's t until t minus 2. So one less leg. All right. If this happens, or if you consider that it's a matrix with rank 0. Finally, if the rank is in between the amount of variables you have, and 0, so in between 0 and the amount of variables you have, in our case between 0 and 4, we're doing this transformation. So we will use the function vec2var, which comes from var's package, vec2var. So transform a vacuum to var in levels. Then this vacuum is coming from the Johansen function that we used before. So ca.jo or yo, using our data, and then for the amount of legs p, but then we're adding this r in here, which is the rank. Let me see if it's telling us in there. The co-integration rank. The default will be 1, but in here we're giving the rank to them. Okay. So that's it. In the end, no matter which model we got, we're just extracting the number of legs, the rank that we're dealing with, AIC of that model and BIC, and constructing our IC vacuum there. So from 0 until 6, we have 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. In total, we will have 20 models in our matrix. All right, let's go. Now let's get the top 10 for AIC, top 10 from BIC. And when we take the intersection of AIC and BIC of the top 10s, we get IC int. We get this 6 guys only, which will be just 3 and 4 legs, and will be ranked 2, 3, and 4. And look how interesting it is. It didn't pick in our top ones, at least combining AIC and BIC, we don't have 0 and 1, which agrees with the results we had from our Johansen procedure here. We were rejecting the r equals to 0 and equals to 1 for the 3 leg lengths, and this kind of agrees with it. It's probably not the case all the time, but it's an interesting thing to notice. All right, let me go back to the slides. So we generated, got the top ones. Next step, this is what we have. Next step, we will be testing for the vacuums using the Bruch-Godfrey test once again. As we did before, it works for, same way it works for var, it works for vacuum. So adequate set is just getting arranging in this matrix of intersects, and then a match to find. This is pretty much the same as we've done before, and do the final do a final check of the residuals. So let's go. Number of models equals to length of our index, which is just 6 models we're going with. Then P will receive adequate set vacuum I1. So inside of our adequate set vacuum, we're just looking for the first column to get our P. R will be the second column. Then we will print checking vacuum PR. So we will be printing this part here in that line. And finally, print serial test. We have used it before from library vars, if I'm not mistaken. And then the model we have, which is being pointed here, we're telling them once again, it's legs Bruch-Godfrey equals to 1, and the type of test, Bruch-Godfrey. That's it. Look at what we get here, and I've put them away in our slides. We have 1, 2, 3, 4, 5, 6. If I click, you will see once again, we're moving forward with vacuums with 3 legs and 2, 3, and 4, rank 2, 3, and 4, or maybe I should say integration rank 2, 3, and 4. And we are still moving forward with 4 legs, although, as you can see, once again, we have this p-value that is in between 1 and 5%. So yeah, that's what we're doing here. We are rejecting 1%, but not a 5%, but still moving forward for this one. Okay, so this will be our adequate set of vector error correction models with leg length P and rank R. Now, after choosing those leg length, we will have to choose a reasonable leg length P. Oh, spoiler alert, it's going to be 3. That looks much better in here. And using a subset of specifications with P equals to P star included in the adequate set of vacuum models constructing question 3, I'll obtain inference on all possible equilibrium relationships. Please use the identifying restrictions, and then you have here beta equals to the identity of R, beta, etc. And where beta tilde is this interaction here, the n, the number of variables, minus the rank times the rank. All right, let's go. Look, let's go there too. Question 4. Now, we're choosing leg length 3. And for rank, co-integration rank from 2 until 4, which is what we have. We are running these lines. And let me have one of them there in the screen. So first, we're doing a vec PR, where we're taking this specification transitory from CHO, so the same type that Johansen test trace, putting in vec PR. Then we're getting this beta, which we're using this other function CHOs, so OLS regression of the vacuum, and just we're taking the beta and saving it in here. This is a very specific thing. You will be able, just pay attention if you're using it for your report. The number of co-integration rank should agree with what you found before, and the number of legs should agree with what you found before. And I think that's about it that you need to change in this code. You don't need to mess with any of the rest there. So beta PR, I will be saving its BP values PR, and then this one is receiving an ace. Then for I in this little thing are the number of restrictions plus 1 until the number of variables. We will be doing this calculus here. H receives a beta PR that we got before, then Hij inside of, where's Ij? Inside of this loop here we're dealing with will receive 0, and then we're doing a VLR test of a vec PR HR. If we go here, likelihood ratio test for restrictions on beta. Okay, quite a specific thing, but the important thing, what's going on here, it will return us this guy for our vacuum 3.2, and we will return this guy for our vacuum 3.3. One important thing, we are not dealing with 3.4, although we chose to have 4 there. You will see we're just doing it for ranks that are below the amount of variables we have, because if we have the same, if R is equals to 4, which is the amount of variables we have, it means it's just the var. It's not a vacuum. There are no restrictions, so that's why we don't need that one. So this is what we did here. This was what we got as a result, and let's go interpreting this guy, because I think this falls into something that can be more challenging to get your head around it. Last time in tutorial 6, we were dealing with the 4 variables in a univariate way. Now we're getting the 4 variables here in a multi-equation way, not univariate, but unit equation. Now multi-equation, right? Let's go. So for the first one, you see, we will begin with co-integration rank equals to 2. So we'll have this first here. So first equilibrium relationship. I try to put some color here so we can point to what we're talking about. First, if you remember from our test in tutorial 6, we were quite confident that I90 was an I0 process. So we reject the null hypothesis of the presence of a unit root in the process of an I90 process, right? So this one suggests that there is an equilibrium relationship between I90, I3y, and I5y. I painted this one pink, just to tell you, when you see a very low value here, for this test, it means it's equals to 0. So nothing relevant in here. So just assume this guy is also 0 because it's a very small value. So that's it. What we're looking at is that there is some value for these 3 guys. How can we interpret that? So suggest that I90, I3, and I5 are related in equilibrium. Consequently, since we think this one is an I0, either I3 and I5 are both I0 processes, or they are both I1 and they are co-integrated. Because in the end, the combination of these 2 guys, the combination of these 2 guys and this one is an equilibrium. And since this one is an I0, since I90 is an I0, this combination should also be an I0, so they are in equilibrium, which makes you think either both of them are I0 or both of them are I1. Okay, so this is a little bit what is happening when we're trying to interpret the results from this first one, from ECT1. All right, let me clear that one. This is the first part. So then we have, following on with that one, if both are I0, then we would have 3 I0 variables, which contradicts the fact that we must have at least 2 I1 variables in here. We need at least 2 of them being I1. Hence, the only viable implication is that I3 and I5 are co-integrated processes, both being I1 and co-integrated. So this is what we're concluding, that these are co-integrated. Yeah. You will see that we have, let me go back here. We have to have 2, we have to, for this one, for the rank 2 matrix, we need at least 2 I1 processes in this list. And for rank 3, you see here, we need at least 1 I1 process. So that's what we're considering, okay? That's why we have we need 2 I1s in here. All right, let's keep on going. Second, our second equilibrium relationship here. So 0 for the I90. So there should be an equilibrium relationship between these 3 guys. So combining these 3 should end up with an I0, combining them somehow. So let's clear. So just the I80, I3, and I5 are in equilibrium. Since I3 and I5 must be co-integrated, based on this one, these 2 guys must be co-integrated. So we already know I1 and I1. Hence, the only viable implication, oh no, sorry, since I core integrated, oh, sorry, the second equilibrium relationship labeled are related in equilibrium. Since I1, I5 must be co-integrated, our I80 cannot be I0. If that was true, then there would be only one common stochastic trend, which again contradicts the fact that we must have two stochastic trends. So this I1, and this I1 here too for our second one. So combining the analysis of this one and this one, we conclude that this is what we have in there. All right. This leaves us with the possibility that all three are I1 and all three of them are co-integrated. We have, however, in this case, we have referred to linear independent co-integrating relations, which again means there is only one stochastic trend present. We see that if we start with I90 equals to being an I0 and I equals to 2, then we always arrive at a contradiction, right? And this means that our inference from vacuum R equals to 2 leads us to conclude I90 equals to 1, which clearly not compatible to what we did in tutorial 6, where we found that I90 is an I0 process. So it will happen sometimes that they will contradict each other. The ADF tests that we did for the single equation will contradict the results that we get from this one. And yep, we need to use our knowledge to try to decide the best way of interpreting. For your report, as long as you explain something, you should be good. You don't need to have a professional analysis of it. That is not expected. So you don't need to go crazy if things are not agreeing with each other. This can happen. Let's move to the third, to the one with 3. So now we have, let me put it here. Now we have 3 equilibriums because this is rank 3 vector error correction model. So for the first one, let's start there. At least one must be I1. At least one of them must be I1. Once again, I painted in pink the zeros. So this first one is saying that I90 and I5 are in equilibrium. Since I90 is an I0, then I5, we infer that I5 is I0 also with a high degree of confidence. So I0, I'll just put it like that, I0, okay? Then for the second one, it's an I80 and I5, there is some equilibrium. There is an equilibrium relationship between the two of them. So since we just said that I5 has to be I0, then so does I80. So I0 and I0. You can see it's already quite in conflict with what we just said for the previous one. Then because there must exist at least one process, by now we are already pointing to this guy being an I1. But unfortunately, equilibrium relationships on ECT3, which are saying that these two guys are in equilibrium, lead us to conclude there exists an equilibrium between I3 and I5 with high degree of confidence. This is again a contradiction since there cannot exist an equilibrium between I0 process and I1 process. A few things going on there. You can see the contradiction happening. And if I would summarize, probably the issue we have is that in tutorial 6, we said that this guy is I0. And we start in all our analysis saying that this is I0. And this is probably causing out the issues, because if this was an I1, things would make more sense in the end. you will notice. If you redo the whole analysis, considering that I-90 could be an I1. But let's keep going. We went through the 3 of them. What else do I want to tell you about it? It looks like imposing rank restrictions on var leads us to inference and not that inference that is not compatible with the inference that we obtained from the augmented Dickfuller test from tutorial 6. Pretty much that. Once again, if we had a different conclusion from I-90, I believe things would make more sense there. That is it for question 4, which it analyzes the equilibrium. But I think the most important that we will be looking for your report is what comes in question 5. So finally, let's go to this one. Compute impulse response functions, our IRFs, for a 5-year horizon using a Cholesky decomposition for all the specifications in the adequate set of vacuum models. So last week we did IRFs for VARs. Now we're doing for vacuums, and you see that they are pretty much the same. We'll use the same IRF function. Compare this IRF to those obtained from unrestricted VAR models. Comment on your findings. Let me see. This is what we're doing. Let's go to our R code. Quite an analysis there for our question 4. But finally, let's go. The names, the number of models, which is 6. Then we will be running I and J, which are, let me see, combinations from 1 to 4. Both of them talking about the 4 variables we have. It's pretty much the same, once again, pretty much the same thing that we had last week. So I will be the responses. So we're running this I-90 response to a shock in each of them. And J will be the shock or the impulse. So we'll be in here. First, we'll get how many legs we're dealing with. You will see things happening here. Then we will be dealing with which cointegration rank we want. It will be saving in here. And then first we do this title. So it's vacuum, P and R are in here. And then response of, for example, now we're running I-80 to a shock in I-80. Then you see now it's a shock in I-3 here. So that's how it's running there. Then we will do an IRF, and this will be using this impulse response function that we had before. So vacuum estimate, adequate index vacuum for each of the models. So just the list of models we had before we're taking it. Number ahead, you will see for 40, horizon of 40. In fact, they are asking for a 5-year. Let me fix this one. I will update the code I'm sharing with you guys. Okay, I've just updated. So now it's 60 for 5 years. But yeah, pay attention to the amount you'll be asked to forecast. Then responses from I and impulse from J. Pretty much here, boot equals to true, same thing we did before. And then this little, first, the plot we're doing, and it will appear in here. And our cat is just this guy here, indicating how far we are in running all our IRFs. These are how many? 4 times 4, 16 IRFs times 6. That's quite a few IRFs, right? 84, is that right? Something like that. But you will, that's not what I want. Let's go. You will be able to go through all of them, but putting them together, let's just point a few things that interest us. I've put a couple of them together. First, look at this one. For example, consider responses of I-5 to a shock in I-90. So I've put it here. Response of I5 to a shocking I90. And then have a look at each of the vacuums we're considering here. And these are 3 legs. These are 4 legs. This is for co-integration rank of 2, co-integration rank of 3, co-integration rank of 4. What is special about these guys here? Co-integration rank of 4, nothing different than our VAR, the unrestricted one. Because if the co-integration, once again, sorry for being repetitive, but if the co-integration rank is the same as the number of variables, therefore we're not putting any restriction. So that's what we have in here, and that's what they asked there. Compare these IRFs to those obtained from an unrestricted VAR model. Okay, so have a look. All of them start pretty much the same, going up. It's pretty positive. It touches the 0.2, not different. But look, for 2 restrictions or co-integration rank 2 and 1 restriction or co-integration rank 3, for 2, it keeps on 0.15, while if you just impose 1 restriction, or if you impose no restrictions, it goes back to 0. Okay, so this impulse response function, although it's just an impulse, it changes permanently the value if you're dealing with a co-integration rank of 2. The same is happening for 4 legs. Look, goes up 0.2 for all of them, but it just comes back to 0 in the unrestricted VAR or vacuum with co-integration rank 4 and 3, but not with 2. So this is one of the differences you will see here. And the other one is if you consider a naive approach, etc. Is that one? A similar story emerges from response of I5 to 180. Did I put it all right? No. Where is the other one? Interestingly, responses from I5 to I3 specific shock are more similar between rank 2 and rank 3 specifications, but different in the long run response obtained by VAR 4. So let's go there. Look, they are pretty similar with co-integration rank 2 and 3. But when you have an unrestricted VAR, it approaches 0 a little bit more. So these are things you might be able to identify when you're printing your IRFs. You're putting them together in your assignment. Please don't put the 84 IRFs that you get as a result. Try to get like just a few of them you point, and I believe it will be enough for you to get the full marks. And they say rank specification. I think that's it. Oh yeah. Don't forget also the uncertainties. You'll see that at the end of here, we're talking about being transparent, interpreting the results in light of these uncertainties, far more informative. And whatever things you got that contradicted, one contradict each other, just write it down. Like maybe you didn't make a mistake, they actually contradict. So you write down, this contradicts the other one. ADF test contradicts this Johansson tests that we did here, and etc. And that will be it. Thank you so much for attending, and for most of you watching later the tutorials. We will still have a tutorial next week, which will be more like a consultation and give you guys a hand with your report too, if you need. So feel free to please show up, attend. Don't forget to leave a CCAT for the course and SC tutor for your tutors. And good luck with your report too and quizzes. I might see you next week or in a consultation. See ya.